Hello everybody, welcome to next part about resistors. In this part we're gonna talk about a standard resistor value series, surface mount or SMD resistors, marking decoding, different SMD resistor sizes and TCR parameter in resistors. In 1952, the IEC or International Electrotechnical Commission decided to define the resistance and tolerance values into a norm. These are referred to as a preferred values or E-series. These standard values are also valid for other components like capacitors, inductors, and Zener diodes. The standardization of resistor values serves several important purposes. When manufacturers produce resistors with different resistance values, these end up approximately equally spaced on a logarithmic scale. This helps the supplier to limit the number of different values that have to be produced. By using standard values, resistors of different manufacturers are compatible for the same design, which is favorable for the electrical engineers. The E-series consists of the E3, E6, E12, E24, E48, E96, and E192 series. A higher number correlates to a lower tolerance and a higher precision. Each E-series subdivides each decade magnitude into steps of 3, 6, 12, 24, 48, 96, and 192 values. Subdivisions of E3 to E192 ensures the maximum error will be divided in order of 40%, 20%, 10%, 5%, 2%, 1%, and 0.5%. Also, E192 series is used for 0.25% and 0.1% tolerance resistor. The most basic series within the U range is the E3 series, which has just three values, 1, 2.2, and 4.7. This is seldom used as such because the associated tolerance is too wide for most of today's applications. The next is the E6 series with 6 values in each decade for a 20% tolerance, and E12 series with 12 values in each decade for a 10%, and finally E24 series with 24 values in each decade for a 5% tolerance. The E6 series resistor values are widely used within the industry. They provide a wider range of common resistor values that can be used. Since some values in the E24 series do not exist in the E48, E96, and E192 series, resistor manufacturers have added the missing E24 values to some of their 1%, 0.5%, 0.25%, and 0.1% tolerance families. This allows easier purchasing migration between different tolerance parts. There is also a table for E48, E96, and E192 series that you can find it in internet. In next part, we're gonna look at how to decode surface mount or SMD resistor markings. Unlike true hole resistors, which use colored bands to determine the value, surface mount resistors have numbers and sometimes letters. There are three systems that are used: 3-digit system, 4-digit systems, and EAI96 system. In 3-digit system, the first two digits indicates the numerical resistance value of the resistor, and the last digit gives a multiplier. The number of the last digit indicates the power of 10 by which to multiply the given resistor value. Resistance of less than 10 ohm do not have a multiplier. The letter R is used instead to indicate the position of the decimal point. Here are some examples of values under this system. For example, R10 will be equal to 0.10 ohm. As I said before, resistance of less than 10 ohm use the letter R to indicate the position of the decimal point. 102 will be equal to 1 kilo ohm. The first two digits is 10 and the multiplier is 2. So it will be equal to 10 times 10 to the power of 2, which is equal to 1 kilo ohm. If we follow the system's decoding procedure, R33 will be equal to 0.33 ohm, 472 will be equal to 4.7 kilo ohm, 1R0 will be equal to 1 ohm, and 105 will be equal to 1 mega ohm. The 4 SMT resistor marking scheme is used for marking high tolerance SMD resistors. Its format is very similar to the 3 SMT resistor marking scheme, but expanded to give the higher number of significant figures needed for higher tolerance resistor. In this coding scheme, the first 3 numbers will indicate the significant digits and the fourth is the multiplier. Resistors with values of less than 100 ohms are marked. Utilize the letter R to indicate the position of the decimal point. Here are some examples of values under this system. 0R22 will be equal to 0.22 ohm. 2210 will be equal to 2.2 kilo ohm. The first 3 digits is 220 and the multiplier is 1. So it will be equal to 220 times 10 to the power of 1, which is equal to 2200 or 2.2 kilo ohm. 2R20 will be equal to 2.2 ohm. 2203 will be equal to 220 kilo ohm. 10R0 will be equal to 10 ohms, and 1000 will be equal to 100 ohms. Recently, a new coding system has appeared on 1% SMD resistors. The first 2 numbers will tell us the 3 significant digits of the resistor value depends on a lookup table, and the third marking a letter will indicate the multiplier. Let's look at some examples under this system. For example, 01Y will be equal to 1 ohm. 01 from lookup table is equal to 100, and Y, which is the multiplier from letter multiplier lookup table, is equal to 0.01. So 01Y will be equal to 100 times 0.01, which is equal to 1 ohm. The next example is 26Y. 26 from lookup table is equal to 182, and Y, which is a multiplier, is equal to 0.01. So it will be equal to 182 times 0.01, which will be equal to 1.82 ohm. If we follow the system's decoding procedure, 30X will be equal to 20 ohms, 55A will be equal to 365 kilo ohms, 80B will be equal to 6.65 kilo ohms, 94E will be equal to 9031 mega ohm. There is also some notes that can be helpful and will help you to read some particular SMD resistors values. A SMD resistor with a marking of 0, 0, 0, 3 of zeros, or 4th of zeros is usually used as a jumper in circuit boards. A cheap resistor marked with the standard 3 digits code and a short bar below the marking denotes a precision 1% or less resistor with a value taken from E24 series. For example, 122 with a short bar below the first two will be equal to 1.2 kilo ohms with 1% precision. SMDs with values in order of milliohms made for current sensing applications are often marked with the help of the letter capital M, M or L, showing the decimal point location with value in milliohms. For example, 1M50 will be equal to 1.5 milliohms, 2M2 will be equal to 2.2 milliohms, and 5L00 will be equal to 5 milliohms. Surface mount resistors come in a variety of sizes. The length and width of an SMD resistor case can be identified by the package code used. For example, an Imperial 0805 resistor case will have length of 0.08 inches and a width of 0.05 inches, while an Imperial 0603 resistor package will have a length of 0.06 inches and a width of 0.03 inches. The imperial code is more commonly used in the PCBA industry. The table below lists the different commonly used resistor packages. In this part, we're gonna talk about MELF resistors. MELF resistor, or metal electrode leadless phase, is a subset of SMD resistors with a cylindrical shape that is metallized at its ends. They are used in high precision applications since they have a low failure rate, high moisture resistance, and are able to withstand high temperatures. There are three main MELF packages: micro MELF, mini MELF, and MELF package. You can see these packages' dimensions in below table. In next part, we're gonna talk about TCR parameter in resistors. A resistor's TCR, or temperature coefficient of resistance, tells how much its value changes as its temperature changes. It is usually expressed in ppm, or parts per million, per degree centigrade units. But what does that really mean? Let's have an example. Assume that we have 50 ohm resistor with TCR of 20 ppm per centigrade. That means its resistance will not change more than 20 divided by 1 million, which is equal to 0.0002 ohms per ohm per centigrade temperature change. In our case, if our resistor heats up from room temperature, which is 25 centigrade, to 50 centigrade, so to find our resistor maximum change, you should multiply 0.00002 times 50, that is the resistor value, times 25, the temperature change, that will be equal to 0.025 ohms. So your resistor value will be 50.025 ohm at 50 centigrade. In typical applications, it's not very important, but in some sensitive case, you should consider this parameter. For example, if you have a sensor that its output is current, not voltage. So if you want to measure the sensor value, you should convert it to voltage to measure this voltage bar, for example, microcontroller ADC unit. To do that, you can pass this current through a resistor. This resistor is called Shunt Resistor. Some sensors' output current is just from 0.1 milliamp to 2 milliamp. So if you assume that we are going to pass this current through a 1 kilo ohm resistor, and if your resistor have a high TCR, you're gonna have some problems here. Because if temperature changes too much, you can't have precise sensing, right? But in your typical applications, for example, pull-up resistors or voltage divider resistors, it's not a very important parameter. Thank you for watching this video. Please subscribe to my channel and like the video if it was useful for you. I will see you in next video.